In this video we are going to look at the three possible fates for the universe and how we can use them to derive a formula for the critical density of the unvaries, where the fate flips from being closed to open. Let's look closer at the possible fates for the universe. We're going to plot a graph, showing the average separation of galaxies against time. If we draw a line for the present day as well. There are three possibilities for the future of the universe. Firstly, if we live in an open universe, where the universe keeps on expanding forever as the kinetic energy of the galaxies moving apart is greater than the gravitational potential energy trying to pull them together. Secondly, if we live in a closed universe, the gravitational potential energy is greater than the kinetic energy, so the galaxies will reach a maximum expansion before gravity wins and pulls them back together at what is known as the Big Crunch. Finally, we could live in a flat universe, where gravitational potential energy and kinetic energy are balanced, meaning that the expansion continues on forever but it slows down until at infinite time, the galaxies stop moving. If we think about these in terms of the density of the universe. For a closed universe, its density is high, so greater than the critical density. In the open universe, the density is low, so the density is lower than the critical density. Finally, in a flat universe, the density is just right and is equal to the critical density. Now let's look to use these definitions to derive a formula for the critical density. A quick recap of our definitions for each scenario. Open, kinetic energy is greater than potential energy, flat, kinetic energy is equal to potential energy, and closed, kinetic energy is less than potential energy. Now if we are defining critical density, the open and closed scenarios are no use to use, so let's remove them. From our definition we get that potential energy is equal to kinetic energy. Using our standard formulas we get this equation. Hubble's law relates the velocity of a galaxy to its separation distance, so we can substitute this into our energy equation. From here, we can rearrange and group terms, cancelling one of the mass terms as we go. Now to remove the term for the mass of the universe, we can think about the density of the universe. Assuming the universe is spherical in nature, we can get a formula for the mass of the universe in terms of its radius and density. If we substitute this in, we can now rearrange our formula to get the critical density as the subject. In our final piece of cancelling we get our formula for critical density to be 38ths times h0 squared, divided by big G times pi. Now if we assume Hubble's constant to be 70 km per second per megaparsec, we get the critical density to be 9.5 times 10 to the negative 27 kilograms per meter cubed, which is approximately 5 protons per cubic meter. This is roughly what the observed density of the unvaries is, so scientists currently think the flat future is the most likely. However, all this work has large error bounds, so there is much debate whether the universe is flat, open, or closed. As the impact of dark matter and dark energy is further researched, these will also be included in this formula. Hopefully this video has helped with this derivation, and thanks for watching.